This is a presentation of the 19th Annual Colorado Snow and Avalanche Workshop, a program of the Colorado Avalanche Information Center, Friends of CAIC, and the National Avalanche Center, presented by Dinafit and Pomoka.
Hello, my name is Robert de Boer. I'm a professor of aviation safety and also the campus director here in Amsterdam for an English university based in Newcastle called Northumbria. And today I'd like to share with you some learnings from incidents in the aviation sector to see whether that is worthwhile for avalanche prevention. Why would we want to learn from aviation at all? The two industries seem to be so separate. But don't forget that our industry, aviation, has taken a long and rocky road to get into the realm of ultra safe that we are now, with only one fatality every 9 million flights or so. And who knows, that might be the safety record in future for avalanche workers as well. So let's get started. Imagine looking outside your window when you're flying high from Europe to America, and you see that the engine looks like this. Wouldn't you get a fright? This is a so-called uncontained engine failure, which means that many parts of the engine have spread across and have not been contained within the whole the cover of the engine itself. This happened on September 30th, 2017, with an Air France A380 aircraft flying over Greenland at the time. 521 people were on board, and luckily there was no further damage to the aircraft itself. The aircraft is designed to continue flying on 3 engines, so that wasn't in itself a problem, but it did make an emergency landing over in Goose Bay. And what we need to know when something like this happens is what was the cause of the accident. And we cannot do that without finding all relevant data. And so one of the things that had to be done was to find those missing parts of the engine that flew off the aircraft at the time. And here, in the end, they were able to find the so-called fan hub, which is the part which contains some of the turbine fans, under the several meters of snow in Greenland. And it took quite extensive searches to make that happen. Once that part was found, that component was found, it was possible to analyze it. And eventually it was found that the fatigue crack was located in the center of slot 10. And the investigation authorities believe that cold well or cold creep fatigue triggered the fracture. The fan hub is manufactured from a titanium, aluminum, vanadium alloy and wasn't previously thought to have been susceptible to this sort of damage. So this was a new learning from this incident. Here's another engine that was uncontained when it was damaged. This is QF32, part of the engine of the QF32, again an A380, which was on its way from Singapore to Sydney when at 7,400 feet, this engine exploded, you could say. It had 468 passengers on board, and at 7,400 feet, they heard boom, boom, and this was the result. Of course, the pilots couldn't see this, nor could anyone on board because it was under the wing. But this is what they saw from the top, from the windows in the cabin. You can see quite a lot of damage here, and in fact, in this case, the fuselage was heavily damaged as well. Again, a lot of technical investigation was necessary to conclude what the cause of this failure was. In this case, it was the breaking of a stub oil pipe, which had been manufactured incorrectly, so that the thickness of the walls was much thinner than it had been designed for. And so we see in both these cases that it's really important to get the technical facts right and to keep delving and spending a lot of money to make sure that we know what technical aspects played a role in the incident. But it isn't just technology that we need to understand. We also need to understand why things make sense to the people that are involved. What you see here are the tracks of a Boeing 737 from KLM at Schiphol Airport. And you see how the green path, the aircraft takes taxiway Alpha to take off from runway 36C, 36 center. But the pilots mistake themselves and actually start their takeoff run on taxiway Bravo instead of continuing on to get to the real runway. And they actually did take off from the taxiway and continued without any further problems to their destination in Warsaw. And this is KLM, this is Schiphol Airport in Amsterdam. So this is their home airport. And you can imagine that trying to understand why these pilots made this mistake is really an important part of any investigation. And this is a page out of the analysis report, the incident report, where you see in much more detail what happened at certain points in time when the aircraft was taxiing towards the runway and starting to take off. And it makes then all of a sudden a little bit more sense. We can place ourselves in the heads of the actors, of the pilots, to understand why it made sense to them to act as they did. The aircraft was de-iced on the apron on the left-hand side, where you see the PHBDP standing. That's the de-icing platform, and there was light snow on the taxiways. This was in February in the Netherlands. Air traffic control instructed the aircraft to taxi to the departure runway via taxiway Alpha, which they did, of course. But that was against the prescribed direction of travel. Pilots with a home airport are much more used to go in that direction using taxiway Bravo, the one which is parallel to Alpha and one lower down. They had a reasonably high workload, and then the yellow track shows a Chinese aircraft that was lost and stood in the way of them towards the crossing of Whiskey 9, W9. So they had to take an earlier corner, Whiskey 8, instead of what they had been told beforehand, and therefore they had to reprogram the computer. And it seems like they thought that coming down Bravo and taking a right turn and then a right turn again would bring them to the runway, like it always did. But now, of course, they were on taxiway Alpha instead. They took a right turn and a right turn again, and thinking they were on the runway, they started their takeoff run. And all this time, the air traffic controller wasn't actually monitoring their progress. And so he didn't notice that they were taking off from the taxiway instead of the runway until they were going so fast that it had no use to stop them again. So having this detail in the investigation all of a sudden allows us to understand why it may have made sense for the people involved at the time to do as they did. And that's an important step in understanding what is happening and why a particular incident has taken place. Based on all this information, we need to draw conclusions and generate recommendations. And one way of doing that is to use an Ishikawa diagram or a fishbone like you see here. And what this shows you is there's never a single cause for any incident. There's multiple causes, which, easy to remember in this case, these are all M's, might include measurements, material, machinery that's available, the methods that we're using to do our work, the manpower itself, and certainly in the case of aviation and avalanche safety, Mother Nature. And notice also that some causes are dislocated in time and geography from the incident. Materials will have been defined beforehand, methods will have been defined beforehand. And just as the case of the taxiway takeoff, where the air traffic controller was involved in the incident, but dislocated from what happened. And choices in runway markings and taxiway markings influenced the possibility for the pilots to see where they were going. Those choices are dislocated from the incident itself. And those causes we must not forget. Sometimes there's no cause to an incident. This is United Flight 1549 landing on the Hudson in 2009. You may have remembered that. The aircraft lost both engines after striking a flock of birds. And in aviation, it's weird, well, not very weird. Engines are able to withstand birds, but only of a certain size. And these birds were bigger. These were geese, Canadian geese, which were bigger than the constraint which is put on birds for which an engine should be immune. And secondly, aircraft are always designed to be able to fly with at least one engine out. But of course, in this case, both engines had been hit by birds, and so both engines flamed out. And so both constraints were violated in this case, making a powerless landing, or ditching as a landing on water is called, inevitable. Finally, when we've done our analysis, we know why the actions make sense to the people involved, and we've defined what we feel are the causes of the incident. We need to disseminate our learnings. And this, of course, is a picture of your own avalanche review, which would be an ideal medium to disseminate this sort of learning. In summary, learning from incidents means that we need to get the technical facts, understand why it made sense to the people involved, draw conclusions and generate recommendations, and then disseminate our learnings. All in the effort to not let things like this happen again. And that means that the learnings and the conclusions and the recommendations that we've drawn up, we need to train our people with those. We need to coach them on the job to understand how it impacts them in their daily work. And we need to finally challenge them when they take these lessons unheeded. That is the only way that we can make sure that all of the effort that we've put into an investigation actually benefit the people on the ground to prevent things like this happening again. All of this has been based on an incident happening, but we can also be proactive about safety. And that is sometimes referred to as safety 2. What we need to do is consistently report near misses and investigate them as if it were a real incident to see what we can learn. Build collective wisdom out of these. We also need to understand why things go well, because things usually do go well. And that helps us to understand what we need to enforce. We can innovate, surely, certainly from lessons that we have learned, but we need to control these. We need to do this under controlled circumstances so that we can properly understand whether our intervention has the effects that we thought. And then we may need to create rules or best practices if these interventions turn out to be really useful. I hope this presentation has been useful and has shed a little bit of light on how we investigate in aviation and how we might make that useful for avalanche safety as well. Thank you for your attention.